Welcome to 10x Engineering. This talk is presented by Urban Company, Asia's largest platform for home services.
Everyone, my name is Abhishek, and I've been in this industry for more than 6 years. And from the past 2 years, as I was fascinated with data, I'm trying to create platform that leverages data, which caters again the business use cases. Today, in this talk, we are going to focus what were the challenges that we faced uh, during the during the phase where Urban Company has scaled from, let's say, 100 engineers to 200 to 300 engineers. There were a lot of use cases that came around, and what are the challenges that we faced during this time and how we solve these challenges by creating a democratized data platform. So let's just first go through what are the use cases that we where we use data in our application. So whenever customer opens Urban Company's application, the main use case is to book a service and then directly get the required service. So what do we do here? So we show top category. We automatically show top categories on the home screen so that the customers, what the customers is most likely to book. This helps. This reduces friction and helps in the booking journey. Next, let's say the customer has already selected the, let's say, haircut service and they want to choose that. And once they move to the slot screen, there we automatically show only the slots that we would be able to fulfill. So instead of showing all the slots which end up might not be able to fulfilling it, we only show the slots which can fulfill. This would obviously improve the user experience. And at the end, during the checkout page, we automatically select the best payment method which the user has frequently used and which has the most success rate. Here we have seen that data use cases are pretty much everywhere, and the basis of serving with the data, we have to first of all pipeline all the data that is scattered throughout the Urban Company. So first of all, we need to pipeline this data into our warehouse, then only we can perform analytics on that data, obviously. So let's go through the basic and let's see how we are pipelining data from these sources to the warehouse. So in our case, we have multiple sources. One being our customer and partners app. The other is third-party application like AppsFlyer. We get a lot of events from there. And from the backend service also, we generate a lot of internal events that also needs to be pipelined. And last but not least, we are having transactional DBs where where it shows the transactional data. We are using Mongo and MySQL to store this kind of data. So we have created an in-house data event service which ultimately exposes APIs which helps in pipelining data from these applications. And for transactional DB, in order to extract data from there, we are using Kafka connector, which does nothing but work similar to how a replica gets data from primary node. It does the same thing. It gets data from the secondary node and extract it, and then ultimately both the services pipeline this data onto a message queue. In our case, we are using Kafka for this. After all the data is there on Kafka, so up till this point, we can see that everything is running in real time, and all the data at this point of time gets accumulated into Kafka. And given we need to pipeline this data at the end into a warehouse, we have to have some kind of processing, and given the volume of data is so huge, so we are using Spark over here so that we can enforce we can do transformation if need be, we can enforce schema if need be. Transformation can be as simple as converting epoch to date time and so forth. So here we have created, based on the required frequency, we have created the Spark jobs. Here in this Spark jobs, our first job is to pipeline the raw data onto the S3 so that because we know that if we do anything with the data, it can break. So it's much better to do nothing with the data and directly pipeline the raw data onto S3. And then after we are sure that, okay, we can do some kind of processing over it, we do that and then create base tables onto our data warehouse. Now we can see that the base tables from all the sources, we have gathered the data and created the base tables. Now the basic use cases that comes into picture is, okay, we need to create one dashboard and use these tables to create that dashboard. One use case can be, we want to show revenue for whole Urban Company. Now, in order to show revenue for the whole Urban Company, obviously there will be multiple sources. Probably we need to get the commission revenue, we need to get we need to get the platform fee as well, and there are miscellaneous other things that from where we can generate the revenue. Obviously here we can see there is just not one table from where we can directly get the access. There are like multiple of tables from where we access the data, and hence we have to have joins between these tables and denormalize the data and then query this data onto our dashboard, which means if we directly use the query in this dashboard, obviously this query will be huge. It is joining on a lot of tables, and it will going to take a lot of time. So what we do here, we create derived tables, and that's a common way. That's how the other places also people create tables. So ultimately we join all these tables and create the derived tables, which ultimately helps us in serving this dashboard with the in seconds of latency. So before going further, let's understand how we are able to create these derived tables in the current platform. So in the old platform, what are we doing? There is, we had standalone instances, and then we used to write Python scripts. With that Python scripts, we used to take, as we were saying, that we were consuming base tables, and with the base tables consuming that, we used to joins and do the transformation, all the things required, and then we were creating derived tables with that, using those Python script and pushing those derived tables onto our data warehouse. Once the data is available in the data warehouse, as we can see, we can use this data for any use case. For ad hoc purposes, if we just want to analyze certain things, we can use Redash. In our use case, we are using Redash, and for dashboarding purpose, as we have previously seen, we are using Superset for all the dashboarding needs. So up till this point, we are able to cater to all the analytical needs. Obviously, we can create the dashboard and everything, and if the dashboards are internal, so it's fine that it takes like few seconds to load. But let's say that the same metrics, if we want to create for customer, let's say we want to create for partner, then obviously we are showing it on the application, and it has to serve in ultra low latency, like it should be served in 100 200 milliseconds. So what do we do for that? Obviously, we can't query a data warehouse. It would take seconds to get the data. So what do we do? It's a simple pipeline that we have created. So over here, we have created a simple pipeline where we gather data from data warehouses, and each individual team bases their use cases. Let's say we want to create partners metrics. For that, there is a certain team which in their microservice, they are writing Node.js scripts, and then getting these derived tables and creating metrics according to their use cases. So ultimately, they create the metrics and then put it onto a transactional DB, because querying a data warehouse would take time, so it's better to transform whatever the transform needed to transform the data and pipeline this data onto a transactional DB. Once the data is there in the transactional DB, obviously the latency is which be much better, and then we can serve our use cases. And similarly, because in this as of now in this platform, no team is able to talk to each other, and there is no platform where we are exposing like these are the metrics that already exist. It can happen that the other team also has similar kind of use case, but with more metrics. They can also end up creating more scripts where they are also creating more metrics, but same metrics can also be created by them as well, which ultimately leads to duplication. And let's say if third teams comes out and they also have the same kind of use cases, what do? They either create their pipeline, or do they use the existing sources? They don't know, because already we have duplicated the metrics. So up till this point, we have seen that we have created derived pipelines as well as transactional pipelines to cater to our internal dashboards as well as to internal ad hoc analytics use case plus transactional use case. But there were obviously a lot of challenges that we have faced during this journey. We are going to discuss these challenges one by one. So just to refresh, what have we done till now is we are using Spark jobs to create base table, and ultimately using the base tables to create derived tables with the Python script. So up till this point, let's say we have lot of scripts which are creating derived tables. Ultimately, the problem that we are facing in transactional pipeline, we are facing here also. We don't know if our existing use case can be served by the existing derived table or not. We don't know that, because there is no platform to search this. So searchability is a major problem for us as of now. And let's just say that by talking to an analyst, I was able to understand that, okay, this use case is fulfilled. Probably this use case, we have to create another derived pipeline for this. So what do we do in that case? In that case, because the complexity is too high to create these Python scripts, what they end up doing is they end up asking the analytics team to create this derived pipeline, and obviously this takes time, and analytics teams only need to create these derived tables. So it's difficult to onboard all the derived tables given the business use case are so many and analytics team members are so little. So obviously either we need to increase analytics people or we need to onboard more people which can power these use case. So let's just say that okay, they got the bandwidth, they were able to create the use case where they created like derived table 2 which uses base table 2 and derived table 1. Now let's just go through what are we doing over here. So in the derived table 1, both the tables needs to be updated at an hourly frequency that is given. So what we have done over here is the derived table 1 updates every 10th minute and derived table 2, because it is dependent on derived table 1, it is getting updated every 20th minute. So as we can see, any delay, if it happen whatsoever for the derived table 1, if it takes more than 10 minutes, obviously it is bound to happen that derived table 2 will not get updated, because we are just updating like after in the 20th minute till the time derived table 1 was not updated. So here, if this issue happen in our system, there is no way to identify, okay, there is some table where the stale data is there and we are able to understand, okay, this is already happening in the system and there is some kind of alerting with which we can take certain actions. As of now, this is not at all there. What used to happen is people query these tables and they identify by themselves, okay, this is the problem, stale data is happening, probably you should do something about it. So something needs to automatically happen over here to resolve this issue. Next, let's say somebody tells the analytics team this is the problem, this table is not getting updated, but as of now we have not like nothing is accountable and ownership is not properly defined, which means that we don't know who has done the changes, why these changes were done, and did we properly test the changes when we went live with, let's say we have done the changes in the derived table 1, did we properly test the changes, then only we went live or not, did the proper code review happened or not. So obviously these phases would sound similar to how the microservice world works, where we do have such kind of processes and automated processes where these things happens, but in analytics world these things were basic, but these were not happening as of now. People were directly writing scripts and directly deploying out production, which obviously leads to these kind of issues. So let's say here we identified, okay, we talked to our analytics teams and there is an issue in the derived table, we got to know that. Now what do? We have to identify what is the root cause for that issue, right? Here as we are talking here, we know that derived table 1 is the issue, but obviously when we face the issue, we don't know that. So what do? We have to go through the Python script, understand the everything and see what are the sources of the data. Is it issue with this table or is it the issue with all the sources that we are consuming? So there is no top level view which tells me that, okay, this table uses these two tables, this table uses these two tables, and this table is the one probably causing the issue. There is no platform as such for that. So we have to manually do the process and identify the root cause. Ultimately, let's just say we identify the root cause, that derived table was the one due to which we were facing this issue. What can we do in this situation? Okay, let's think about it. What can we do in this situation? As of now, both the scripts are running in their own environment. There is no synchronization between these two scripts. So at max, by default, so obviously derived table 1 at the end, what we can do is we can increase that, like instead of updating the derived table 2 in the 20th minute, probably we can take some more buffer and update it into the 38th minute. That's all what we can do. But let's just say that derived table 1 for some reason takes to more than 20 minutes. What would we do in that use case? So probably this kind of problem statement we have seen in other places also, and people might have, if they are if they know about Airflow, they might know that this problem is already solved, where we are using DAGs and we are creating the lineage for the everything. Let's say in this case, derived table 1 was dependent on 2. We will create a simple DAG, and first derived table 1 will run and then derived table 2 will run. That's simple. But now think that if there are like hundreds of tables gets onboarded onto this platform, and like these tables are interdependent on each other, maintaining this DAG would be like ultra difficult. So we have to have some platform which does this thing for us. So hence, now we are going to talk about what are the possible solutions that we can have to solve all these problems. So the first problem that we were facing in the earlier system is we have to know if our use cases are already being served or not. We have to have some solution for that, right? It is needed that we have to create a data catalog where we can directly search and identify, okay, what is the current current use cases that are already onboarded onto the system. What does it do? Is my use case is able to cater already by the already onboarded tables or not? Without a data catalog, I won't be able to do that. So ultimately, we need this. Next, as I have already said, software engineering practice looks pretty simple. We have to apply it, but analytics world has never seen it, and they tend to manage these things by their own, and this was not there in the earlier platform. In the software engineering practice, obviously, we have to do what do? We use whatever the things that exist in the system, we standardize a lot of processes, we test the code properly, and for this, we have UTs and all. We do proper code reviews, and once we merge the MR, it automatically gets deployed on production. We don't need to do anything. And even for that, if any issues we face, we automatically, the deployment gets reverted. So all the things that we know here have to have in the data platform itself, in the data platform. And on top of this, similarly, there should be some monitoring system which automatically tells me this is the thing that is breaking. You should either have some manual intervention or automatic process should be there to resolve the root cause. Next but not the least, as we have discussed in the last bit, we have to have some unified platform where all the tables which are interdependent on each other, they should be executed in one sequence. Instead of me manually either creating the tag or me manually changing the frequency, there has to be a system which automatically does it for me. So let's see that how we are able to do the same thing. So first, we will talk about how we improved our derived metrics pipeline and made it better. So first problem that we were facing over there is that there are multiple tables that are interdependent on each other. So first thing what we have done is here, instead of every script not being dependent, like we don't know what needs to be executed, here we have combined all the tables in frequency, bucketized them in terms of frequency. So here also we are creating DAG, nothing different over here. So we have created hourly, daily, weekly DAGs for all the use cases to cater according to the frequency. And now natural question comes here that okay, we have combined all the tables which needs to be updated at an hourly frequency, but what do we do when they are interrelated to each other, and how do we make sure that they get executed in sequence? What do we do for that? So in our discovery, while we were exploring this problem, we identified DBT, which automatically does this for us. In a bit, we will show how it is able to identify this lineage, but it automatically, we don't need to do anything. It automatically does this thing. We just need to run one command and it will execute each table in the sequence. And not only that, it parallelizes as much as possible wherever needed, so that not only the tables get updated in the right sequence, plus the tables, if they are not dependent on each other, they get created faster. Next, obviously, the tables once built, they are pushed to Snowflake for further consumption, similar to how it was happening earlier. And we have also created monitoring alerting framework for this. If any issue bases the criticality, if any issue happens in the system, we raise off-genie alert, or we put it onto Slack. If let's say at later point of time we can resolve the issue basis the criticality. Now up to this point, the dependency where we saw one problem where the tables where the tables were dependent on each other. We were able to solve this problem, but the next thing was that we have to bring the software engineering practices right over in the analytics world as well, and because we get a lot of benefits from it. So how do we do it? Here we have created a dev environment where people can build, document each and everything regarding their derived tables. So here we have made it mandatory that they are not just doing any changes, they are testing each and everything in the dev environment, plus they are documenting each and everything, so that at later point we can use this documentation to understand what is happening in the pipeline. After everything is done and tested, again, same thing, same practice we follow over here. We push the code on GitLab. Here we have done a couple of things. Firstly, we have made sure that code is properly formatted, similar to how normal language code is formatted. We check that. We have put certain validation because, okay, we can tell folks that they can document it a lot of stuff, but again, we know that documentation is painful. Obviously, how come we can expect that everybody can write the documentation by themselves? So we enforce it over here. We make sure that people are documenting each table, each column, and following proper standards which we have defined over here. So the validation happen over here, and if they are not fulfilling the validation, obviously the pipeline breaks and they have to redo the things. And hence, because everything is done in GitLab, we can do peer reviews, we can try and make sure that whatever the things that we cannot automate, at least the code review can tell to the person that, okay, these are the things that you can do, probably reuse some components that already existed and do further. Once everything is done, reviewed is done, MR gets merged, and again, same thing. We use Jenkins over here, and automatically the codes get deployed on production. Nothing needs to be done, similar to how microservice works. So here, one thing we have done is before releasing anything on the production, we test our changes on production data, and if any failures happen, we do not make it live on production. We stop the pipeline and revert the changes. So this way, any bugs that could have happened with the new changes, we have resolved it. Obviously, the bugs which happened due to new data, we might not be able to catch them, but the bugs that is happening with the current data, obviously we can catch them and revert the changes. And ultimately, whatever the documentation that we have done in the previous step, we finally push this documentation onto S3, and from there we host this. So till now, we were able to solve orchestration, we were able to solve, we were able to implement software engineering practices. Last but not the least, how do we visualize this documentation? How can people search what exists in the system? So before going to that, let's just go through the code, like how people onboard new use cases. So in code, it's as simple as earlier people were writing simple SQL queries. Here also they don't need to learn any platform or anything. It's all abstracted out. They just need to put the SQL, whatever they were running here only. Yes, they need to do something extra, which I'm going to talk about here. So earlier we told that DBT automatically handles the lineage that we were talking about, where one table is dependent on the other table. So how do it is able to figure it out? So obviously we are specifying this in the code itself, in the SQL query, where instead of directly writing the table name, here we are specifying. We are using a base table that as we remember, we created with Spark job. And same goes for the derived table which we are creating. We are using reference tag, and we are specifying, okay, this is the derived table that we are using. Once we have done all this, DBT knows how the lineage works, and it is able to figure out and run the tables in sequence. And for the documentation part, for each model we have YAML file where we describe everything about the table itself. Description of the table, column description, the ownership which we were discussing earlier, we don't know who owns what. So at the time, we instead of limiting at individual level, we have limited at our vertical level, where we are saying that this metric is owned by, as of now, marketplace. So anything breaks regarding to this metric, we can directly come talk to the marketplace team. This is breaking, please check this. Yes, last but not the least, we were talking about what do we do for the searchability thing? How do we solve this? So we have created one data catalog where people can come directly and search for whatever the things that exist in the system. Not just they can put table names, but obviously they can put all the columns, name, description, basis that it automatically searches and show me the right result. This way I am able to avoid the duplication that could have happened in the system, and also I am able to cater to the simple queries that usually people have. Okay, this kind of data, where does it exist? They can directly go to the system and identify, okay, this data exists in this particular table. Not just that, we have properly made folder structure where the data which is closely related to each other is put it into the right folder, and as well as we have also standardized the naming convention plus the data we keep in our table as of now. So it's simple. Customer related data, you can see from the name itself, it's so simple. Like customer related data, you get it from there, which updates our daily frequency. If you need partner related data, there is one table for that, everything is there. If you need something granular, there is request level table which has everything related to request. So you just need to know the top entity and search for it, and you have all the data regarding that entity in just one table. So the naming convention itself is so intuitive that probably you don't need to go through this searching process itself. You just intuitively know, okay, this is the entity, probably this way I am able to get the required data. And at the end, we were talking about that we were documenting each and every metrics, and here also we can visualize that, and the ownership is also properly defined. And ultimately, if somebody wants to do the root cause analysis, obviously in the orchestration part, DBT can automatically figure out this is how the system works, and in this way I need to run everything. But if when we are doing root cause analysis, is there some kind of visualization available? So this documentation already automatically exposes this lineage where we can check, okay, this table is dependent on this derived table, and ultimately these are using these green color base tables. So lineage is properly sorted, and if we want to identify what are the dependencies of a given table, we can visualize and see all the things here as itself. So up till this point, we are able to solve all the analytic problems that we have discussed previously, and similar kind of problems existed for transactional pipeline, but there are something more that is needed, like we should be able to serve metrics with low latency. What do we do with that? So just a refresher, in old pipeline, people were creating duplicate scripts, and with that they were creating duplicate metrics and then powering this use case. Ultimately, the core essence is developer has the responsibility to create the metrics. They don't know where the things exist, and also to write redundant script to do the same thing, pull data from warehouse and put it onto transactional DB. So what we have done in the new transactional pipeline is that we have, instead of folks writing these scripts and creating the metrics on their own, because they can, ultimately they would use their own set of languages, probably everyone don't know that language. So instead of that, they would use existing platform which we have discussed previously. They would use SQL query to create this metrics. So ultimately what would happen is they would use the same platform, and the metrics would be available right in the data warehouse. And the second problem that we discussed, that all the folks would take data from data warehouse and put it onto their transactional DB. So can we do something about it? Obviously, we have standardized and platformized this by creating online metrics service. What it does is it constantly, one more problem that I missed to showcase in the previous slide is that the same problem of linking everything existed in that also, because everything is running independently. Nobody knows that okay, this metric is dependent on this particular table, probably I should execute this script after that table. Same thing exists over here as well. So what have we done over here is this constantly syncs and checks whether particular table is updated, required table is updated or not. Once it's updated, it automatically gets things onto our online data stores. And while creating this platform, we identified that, wait a minute, instead of syncing whole table, probably the required metrics from the table itself onto the MongoDB, it would be much better if we can identify what are the changes, if any metric has changed actually for a given entity or not. That would reduce the number of records that we are updating onto our online data store. And yes, we were able to optimize a lot of things. For our customer entity, earlier we were updating on a regular basis 8 million, 9 million number of records onto our transactional DB. It would used to take 7-8 hours to update it because the resources were limited. Now with this change, we were now identifying, okay, not every customer is placing requests on the platform. Obviously, every metric won't be updated for that customer. So that way, we just only pipeline the incremental update and put it onto the online data. So this way, the updation process reduced from 7-8 hours to only just 15-20 minutes. It was super fast. Now, essentially, if the data is present on online data source, we have exposed APIs with which any microservice can directly interact and get the data. In the old platform, again, we asked what kind of query patterns that generally people have with which they want to query and get the required data. So we have identified two major use cases. One use case where we have seen that people just want to get the required metric for a given customer. Simple use case, key value lookup, and similarly, key value lookup. For this, we have used MongoDB, where we store the metrics and index the collection on the entity. This way the indexes are also limited, and as well as people can get the metrics with the latencies of less than 10 ms. And for the next query pattern that we have identified is that people do, not just people want to get the metric for a given customer, let's just say, they want to get given a range of customers with certain metric values. So ultimately they want to search something. So what have we done for that? We pipeline the same the metrics where they want to do such kind of searches using Elasticsearch. We call it reverse lookup, where what is happening is they can provide metric values for which we search and give out the customers. So let's just go through. Ultimately, the problems that we were facing in the previous pipeline was that everyone was managing everything on their own. Instead of that, what we have done is we are managing it via platform. It is automate everything is done by itself. People just need to come and go and write SQL queries and everything, and they can specify the right configuration obviously, and everything will be automatically created, synced and available right then and there. They need to write any code afterwards. This way we can obviously, we were able to automate a lot of things, but obviously this resolves a lot of issues where things were interdependent on each other. And afterwards, let's just see what are the query patterns, and let's see some of the examples with it. So for getting metrics with key value query pattern, they just provide the entity IDs and get the required metrics for it. For example, let's say I want to understand and see what are the like for a given customer in the checkout process, what kind of payment mode that the customer is more likely to use. For that use case, if I want to identify that, I just provide that the metric keys, like total number of deliveries that the person has taken and what are the online deliveries with which person has taken in the last 30 days. I just get the data, and then with that data I can make the decision, okay, customer is more likely to take online deliveries instead of taking a COD. So I can take decision based on that. And similarly for reverse lookup use case, people, we have like similar to a SQL query where we do select what are the columns that is required, put filters, limit, offset, each and everything is available over here as well. We just need to provide the entity IDs, what do we want, and at the end, what are the metrics on which we want to query and get the required data. So here we can see that we are getting top rated pros with 5-star rating, and we are getting job deliveries for those pros. Probably we can send communication for those pros because they are performing so good that in last 30 days they have delivered so many requests and they are 5 rated in all the requests. So probably we can send some kind of communication for that. So with this, we are ultimately getting the data like provider ID and what are the jobs that they have delivered, count of the jobs that they have delivered. Up till this point, yes, as we have discussed one by one, what are the problems that we were facing, we were able to solve most of the problems, and now fairly every use case that we are seeing is we are able to power a lot of things, and there are a lot of manual efforts that were going on to make sure that everything work as is now has reduced. So let's just see the impact what we were able to bring with these by creating these platforms. So the one major impact that earlier, as we have discussed earlier, that only data analytics team was involved in creating the derived tables. Now everyone knows SQL. It's easy. Even if you don't know SQL, you know you can just directly use GPT models and directly query them and ask them to create the SQL for you. So ultimately, it has become quite easy to write SQL, and with that, now developers can also contribute into creating these derived tables, metric tables, and so on and so forth. So earlier team was less, and now a lot of developers are also contributing and creating this. And not just that, not just we have increased the number of people who are contributing to the platform, we have also reduced the time it takes to create these derived tables and metric tables. How we do that? Obviously, we have automated a lot of process. You just need to write SQL and everything gets tested, deployed by itself. At the end, if the current system is introducing a lot of bugs, what's the point of having this system? So we have to reduce the bugs that exist in the system. So ultimately, the bugs are reduced by 50% because as we have discussed, because earlier we were just sending the changes directly on production, now we are validating the changes with the production data. And let's just say even if the issues happen on production, we have some kind of monitoring where we get, okay, this is breaking, and we quickly fix that issue. So the number of issues also have reduced. Yeah. Thank you, guys. Yeah, I think probably a lot of questions might be there. We can have a Q&A, and if I am able to answer, I will answer.